Very good afternoon. I welcome you all to this live session for the course Thermal Engineering Basic and Applied. This course Thermal Engineering Basic and Applied is an important core course to the students of mechanical engineering, aerospace engineering, power engineering, electrical engineering. I should say this is an important core course to the undergraduate students. And also this course is useful to the postgraduate students specializing in thermal engineering. This course is offered to the undergraduate students of different institutes and rather through different names. In some institutes, this course is offered as applied thermodynamics, and in some institutes, this course is offered as thermal engineering. So the content of this course are designed to include the topics which are typically taught in either applied thermodynamics or thermal engineering courses. In this course, we have discussed about some basic concepts which are really important to know. Rather, these basic concepts are important to know more about the applied components. Considering these aspects, we have discussed basic laws of thermodynamics, combined first and second laws, which are very, very important to understand the processes in different applied thermal units. I welcome you all to this live session, and I believe that you have completed a few modules already. And if you have any doubts, questions to be discussed, particularly in today's session, please feel free to post your question in the chat box, or you can join the session to have some interaction with me. This session is not only the platform wherein you can discuss. As per the course guidelines, we have tutorial sessions and assignment sessions. So you will have a provision of discussing your doubts, questions in these assignments and tutorial sessions. Since the live sessions are specially designed to have a direct interaction among the students, participants, and instructor, shall request you all to post your question in the chat box. As I mentioned, this course is a very useful course to the students of mechanical, electrical, aerospace, power, and production engineering students. In this course, we have discussed about basic part of thermodynamics, fundamental thermodynamics. We have then discussed several thermal systems which are very much important for our practical life. For example, we need electricity, and for that we all know power plants are there. Power plants, from power plants we get electricity. There are several components in a power plant. First of all, we need to know the thermodynamic aspects of the power plants. What are the different cycles used to compare the processes of thermal power plants and then to estimate the thermal performance? We have discussed this part. Thereafter, we have discussed several major components which are integral to the power plants. We have discussed about the hardware of different components. Thereafter, we have solved several numerical problems, essentially to illustrate the concept that we have discussed. Solving a few numerical problems, you will get some insights into the practicality of a thermal system or practical aspects of thermal system. Considering this, we have discussed many applied thermal units like steam power plants. We have discussed about internal combustion engine. We have discussed about gas turbine cycles. We have discussed about a refrigeration cycle. In a steam power plant, the major components are boiler, steam turbine, condenser, and of course, pump. We have discussed about boilers, the different flow cycles in the boiler, several components which are, the mountings and accessories of a boiler and their role, in increasing the performance of the boiler as well as to ensure or to maintain the safety of the boiler. We have also discussed about steam turbines. We have discussed that blade or blading system or blading arrangement is very important for the power output, because in a power plant we are essentially convert energy from one form into another form. We all have studied classical thermodynamics. In classical thermodynamics, we learned energy interaction between system and surroundings in the form of heat and work. So in a power plant, at the cost of some input energy in the form of heat, we produce some energy in the form of work. That heat energy to work, this transformation takes place in the turbine. It's a mechanical device. Nozzles are also very special for the turbine operation. We have discussed steam nozzles as well. We have discussed about blading diagram, and we have tried to quantify the thermal performance. We have solved a few numerical problems on boiler, numerical problems for the turbine operation that will give you some insights into the turbine output. And also we have solved numerical problems on thermodynamic cycles. Those are used to estimate the performance of a thermal power plant. All these, collectively the theoretical part and numerical problems will give you some insights into the operation as well as design of thermal power plant. We have discussed several modifications those are needed for the modern power plant. Now, essentially, if you look at or if you recall the steam power plant or steam power system, you will find that energy conversion is important, and essentially we do apply steady state steady flow equation to convert heat into work, because many devices are not heat interacting devices and many devices are not work interacting devices. So for example, boiler is a device where heat transformation takes place. Similarly, work transfer is there in a turbine. And to calculate the amount of heat is added to the boiler for the conversion of water into steam, or the amount of work which is extracted from the turbine, we need to know the enthalpy drop, because enthalpy is a thermodynamic property which measures or which is a representative measure of thermal energy of a flow system. Because in a power plant, boiler, turbine, condenser pump, all these are flow devices. So I have one question: how to find enthalpy of point H4, S3 is equal to S4 and S3 equal to no, right? So I really do not know exactly where that particular point or state point 4 is located. But from my understanding, if I can, guess that you are asking this question from steam power cycle, if the point 4 is, see, when you are trying to calculate enthalpy at different state points, you should know where that particular state point is located. If that state point lies in the saturation dome or vapor dome, it is two-phase mixture, then you have to apply the rule of mixture or mixture rule to calculate the phase average properties, which is nothing but the weighted average of, say for example, if you'd like to calculate this enthalpy at any point which is inside the vapor dome. Say, for example, for this case, if the point or state point 4 is inside the dome, then H4 is basically the enthalpy of the mixture. You have to apply the mixture rule, and enthalpy at that state point H4 should be the weighted average of the enthalpy of steam and the enthalpy of liquid. So when you are trying to calculate the enthalpy of that state point 4, that is weighted average enthalpy of the liquid and steam at that particular state point, you should know the dryness fraction or quality of the steam, because that we have learned in our basic thermodynamics course. So knowing the quality at state point 4, you can calculate the enthalpy, because that point 4 should lie on a particular pressure line. Inside the vapor dome, we all have studied in our thermodynamics course that pressure and temperature are dependent. So you cannot vary independently pressure and temperature inside the inside the vapor dome. So if you know the pressure, temperature is automatically fixed or locked, and vice versa. So if you know, because to specify the state point, you know two independent intrinsic properties that you have studied from state postulate. So if you know either pressure, then you know the temperature. If you know the temperature, you know the pressure inside the vapor dome. So if you know the pressure at that particular point 4, then you can calculate H4, that is HF at that pressure, plus X4 into HFG, that is Hg minus HF. So HF and HFG, these values at that pressure, you will get from the property table at that pressure. Now you can calculate H4 by knowing the HF at that state, at that pressure where point 4 is lying, and HFG. So these two values you will get from the property table. But what you need to know is the dryness fraction or quality X4. So now X4 you can calculate from S4, because S4 you already know. So you can apply the rule of mixture for the entropy as well. So S4 equal to SF plus X4 into SFG. SF and SFG, these two are the properties at that pressure that you will be getting from saturated water pressure table. Because inside the dome, no matter where that particular point 4 is located, at that state point, water and water vapor will be in equilibrium. So they are saturated. So you will be getting saturated, saturated properties or saturation properties for that particular pressure from the steam table. So S4 you know, so S4 equal to SF plus X4 SFG. S4 you know, SF you know from the pressure, SFG you also know from the pressure. You can calculate X4 from that equation. Calculating X4 from that entropy equation, you apply that X4 in enthalpy equation, because quality of a particular point is also the same, that will remain same. So quality can also be used to describe the state point. So once you know X4 from the entropy equation, you can calculate H4 using the mixture rule or rule of mixture. You can also apply that mixture rule for calculating internal energy as well. Okay, so that you can do. Only one thing you should remember is that at any state point in the vapor dome, pressure and temperature, either any of this property will give you the HF, HFG, SF, SFG, and also UF, UFG. So because pressure and temperature are dependent and both the phases will be in equilibrium. Okay, and from the given value of S4 that you know from S3, isentropic process, that is the assumption that we typically consider, you can calculate X4. Remaining properties you can calculate applying the mixture rule. So I once again request you all to post your question in the chat box if you have any. This session is limited to only 1 hour, and you will be having live sessions further for this course. As I told that in addition to these live sessions, weekly assignment tutorial sessions are there. You also can raise your doubts. You also can post your question to be discussed or to be, replied back to you in those sessions as well. But the live sessions are particularly kept to have some interaction among the students, registered participants, and the course instructor. If both H4 and H3 are in SH region, so if H4 and H3 are in the superheated region, see, if H4 and H3, there is no problem, because see, let me tell you one thing, H3 should be 0.3 should be in the superheated regime, because we need to superheat the steam before it enters the turbine. Now while steam will flow through the turbine, essentially steam will expand, and in the course of the flow of steam we get some work output, because you all know that steam jet, because steam directly steam is not directed to the turbine from the boiler itself. Steam is first taken to the nozzle, and the purpose of the nozzle is to produce some steam jet. High pressure, high temperature steam jet is now directed or impinges upon the blades of the turbine. So there will be a change in linear momentum. So since blades are continuously rotating, so there will be moment of linear momentum about the axis of the blades are mounted on a shaft or shaft axis, so there will be an angular momentum. So the angular momentum will keep on changing, so the rate of change of angular momentum will give you some torque, and if you multiply torque with the rotational speed of the wheel, you'll be getting some power output. We typically assume that the process is an isentropic process, and while steam will come out from the exit of the turbine, you may still get superheated steam, and that is your concern. So if that state point 4 is in the superheated region, then no problem, because you know the condenser pressure, because turbine back pressure is the condenser pressure, right? So the pressure at which steam comes out from the turbine, that is the condenser pressure. So if you know the pressure and if you know the entropy, so knowing entropy and pressure, you also can calculate enthalpy at that particular point from the superheated table. So you should remember that without having a thorough understanding of basic thermodynamics, it is not possible to know applied thermodynamics. So from the name itself, you can understand that is applied, but the component thermal engineering thermodynamics is there. So to define this state, you need two independent intensive properties. So if you know pressure, that is also, an intensive property. And if you know the specific entropy, that is also an intensive property. So knowing these two properties, you can specify the state, whether that particular state point is inside the vapor dome, or if it is on the saturated vapor line, or if it lies outside the saturated, saturated vapor line. There is no problem. You can directly get the data from the steam table. So whether state point 4 is inside the dome, in that case you have to apply rule of mixture, knowing the quality, then you can directly get the, enthalpy. If it is outside the, if it is on the saturated vapor line, so if you know the pressure, at that pressure you will be directly getting the value of Sg or Hg, right? If the point is outside this, saturated vapor line, then you have to go to the superheated table. So from the superheated table, if you are lucky, then you can directly get the data, or sometimes you may require to go for linear interpolation. So I request all the registered participant students of this course who have joined today, or you have, joined remotely. Please feel free to post your question in the chat box. As I said, this session is limited to only 1 hour, and this session is particularly kept only to have some interaction with the course instructor. So please do not hesitate to ask any questions you have already from the modules that you have completed so far. If you do not have any questions for the time being, you will have provision to post your question in the discussion forum, which are conducted on weekly basis. So we shall be happy to give reply to those questions. As I mentioned, that this course is very important core course to the undergraduate students of mechanical, aerospace, electrical, production, and civil engineering. This course is also useful for the practicing engineers, or engineers practicing in different power plant industries, automobile industries, refrigeration and air conditioning industries. So several aspects together with several numerical problems have been solved. Several concepts have been discussed. So collectively, the theoretical discussion we had and the numerical problems will provide you some insights into the thermal units, the thermal system design and thermal system operation. I request you all to post your question in the chat box. I shall be waiting for another 2 minutes. If I do not receive any more question, then I shall wrap up the session for the day. We shall have more live sessions, of this course later on. We shall join. We shall again discuss the doubts or the questions if you will have, because there are many other modules to be completed. And shall request you all to write down the questions or doubts to be discussed in the live session. Live sessions are particularly designed to have some interaction with the instructor, but these live sessions are not only the sessions for the discussion of your doubts and questions. You can have freedom to post your question in the discussion forum, be it a theoretical question, be it a numerical problem. We shall be happy to interact with you all. We shall revert back to you with the possible answer to those queries. I believe there are no more questions to be discussed in today's session. So with this, I would like to wrap up for the day. And I once again, suggest you to go through several modules of this course, numerical problems that we have discussed, and try to understand the procedure or concept of several components. So with this, I wrap up today. Thank you very much.